Hello there. By the end of this video, you should be able to identify molecular geometry and find the corresponding bond angle. If you need to brush up on electron domain geometry, watch the video on that by clicking in the top right before watching this video. Okay, molecular geometry differs from electron domain geometry in that it differentiates between bonding pairs and lone pairs. It'll become more clear once you see the different types of molecular geometry, so let's jump into that right now. A molecule with a linear electron domain geometry has a linear molecular geometry always, so it's pretty easy to remember. CO2 here is one example. For a molecule with a trigonal planar electron domain geometry, there are two possibilities for the molecular geometry. If there are no lone pairs, the molecular geometry is trigonal planar, and if there is one lone pair, the molecular geometry is called bent. For example, SO3 and NO2-, which are both shown here, both have an electron domain geometry of trigonal planar, but SO3 has no lone pairs, so it has a molecular geometry of trigonal planar, while NO2- has one lone pair, so it has a molecular geometry of bent. According to Vesper theory, lone pairs occupy more space than bonding pairs, so they basically push the other electron domains away, which can be thought of as bending the molecules. So that is how you can remember when the molecular geometry is bent. For a molecule with a tetrahedral electron domain geometry, there are three possibilities. We have tetrahedral, trigonal pyramidal, and bent. If there are no lone pairs, the molecular geometry is tetrahedral. If there's one lone pair, the molecular geometry is called trigonal pyramidal. And if there are two lone pairs, the molecular geometry is also called bent. For example, CH4, NH3, and H2O all fit under the category of having a tetrahedral electron domain geometry. CH4 here has no lone pairs, so its molecular geometry is tetrahedral. NH3 has one lone pair, so its molecular geometry is trigonal pyramidal. And H2O has two lone pairs, so its molecular geometry is bent. You can remember the trigonal pyramidal molecular geometry because the Lewis structure will kind of outline a pyramid like this. Do not make the mistake of calling a molecule with trigonal pyramidal molecular geometry bent, because that is only correct if there are two lone pairs and the electron domain geometry is tetrahedral. Okay, that was a lot. So to summarize, if a molecule has no lone pairs, which is this case, and this case, then its molecular geometry is the same as its electron domain geometry. So if there are no lone pairs, linear electron domain geometry means linear molecular geometry. Trigonal planar electron domain geometry is trigonal planar molecular geometry. If a molecule's electron domain geometry is trigonal planar and there is one lone pair, its molecular geometry is bent. If the molecule's electron domain geometry is tetrahedral and has two lone pairs, its molecular geometry is also called bent. And then there's also the trigonal pyramidal case that you have to remember. Okay, so here's three quick questions to practice finding molecular geometry.
Well, you see pH3 is trigonal pyramidal because the lone pair at the top is pushing down on the other hydrogen atoms, which gives it the pyramidal shape. That one, NO3-, this would be bent. And this is bent because while if we disregard the lone pair, it would have a linear shape. The lone pair at the top is forcing the other two oxygen atoms downwards, which gives it the bent shape. Okay, so the molecular geometry for this one is, well, this one will be tetrahedral on account of the amount of the four atoms and four bonds around central carbon atom.
Okay, moving on. Bond angles are the angles between bonds. And there are only 3 angles that you need to know for chemistry SL: 180 degrees, 120 degrees, and 109.5 degrees. A molecule with linear molecular geometry always has a bond angle of 180 degrees because it forms a line on a Lewis structure. A molecule with trigonoplanar molecular geometry has a bond angle of 120 degrees. Vesper theory states that electron pairs repel each other. So if I draw the Lewis structure of SO3 here, with that in mind, you see that the 360 degrees in the center is split evenly into 3 angles of 120 degrees. So that is how you can remember that. If a molecule is bent and has an electron domain geometry of trigonoplanar, like in the case of NO2- here, then you write the bond angle as less than 120 degrees. That's all you need to write, for ChemSL at least. According to Vesper theory, lone pairs occupy more space than bonding pairs, so it pushes the bonding pairs closer to each other, meaning that the bond angle is decreased from just 120 degrees. Also, previously, the Lewis structure shown did not take into account molecular geometry, but now they do to make it easier to show the bond angles. A molecule with tetrahedral molecular geometry has a bond angle of 109.5 degrees. You might think that it should be 90 degrees, but keep in mind that molecules exist in 3 dimensions, so evenly spreading apart these 4 bonds in 3D will yield a bond angle of 109.5 degrees. If a molecule has a tetrahedral electron domain geometry and has a trigonal pyramidal or bent molecular geometry, they have lone pairs, which will push the bonding pairs closer to each other. And so in these cases, you write less than 109.5 degrees for the bond angle. You can think of a molecule's electron domain geometry as dictating the number you write for the bond angle, and the presence of lone pairs as dictating whether you write the less than symbol. For instance, molecules with tetrahedral electron domain geometry all have the number 109.5 in their bond angle, but only if there are lone pairs, like in the case of trigonal pyramidal or bent molecular geometry, do you write the less than symbol here. This is a lot to remember, so check out the Anki flashcards deck in the description if you want to consolidate your knowledge. There is also a worksheet with a bunch of practice problems to help you practice. Okay, that's it for this video. We hope it was helpful.